Welcome once again to the class of topology. In the chapter of separation axioms, we have covered T0 spaces, T1 spaces, and a lot about T2 spaces, and now we are going to prove some more theorems on T2 spaces, that means Hausdorff spaces. So the first one theorem is that, first write down the statement of the theorem. Theorem is, if f and g, these are two functions f and g, if f and g are both functions from a space x top to a space y row, and y is given to be a T2 space, and if f and g are both continuous functions, f is a continuous function, g is also a continuous function, then the set A contains points from the set X, so X belonging to X, such that image of small x is here, image of fx, which is clearly in y, and image of y, which is also in y because y is here. So fx, sorry, not fy, fx and gx, there is no y. So image of x under the function f is in y, image of x under the function g is also in y. So fx is equal to gx. The set of all those points x belonging to the set x, such that image of x under the function f and image of x under the function g, they are same. This set is a closed set. That is what we wanted to prove. There is an extension of this theorem too that we will cover later on, but first we will move on to the proof of this theorem. So let us see the proof now. We want to show that A is a closed set. What we want to prove? We want to prove that A is a closed set, and it is equivalent to show instead that the complement of A is an open set. So what we will prove? Equivalently, we will prove that complement of A is open. And what we will have to do to prove that the set A complement is open? We will take some point x belonging to A complement, and we will try to find a neighborhood of x, or you can say an open set containing x, such that x belongs to that set and that set is a subset of A complement. I am writing here what we will do. I will take x from the set A complement, and I will try to find a set K here such that x belongs to K and K is a subset of A complement, where K will be an open set. If we can find such an open set K satisfying this condition by taking x belonging to A complement, we can easily conclude that A complement is open. And A complement is open clearly means A is closed. So that is our track of proving this theorem. So I will start with taking an element x from A complement. I am rubbing this too because this I do not need it right now. Let x be an element of A complement. What is happening in the set A? In the set A, for every member fx is equal to gx. and X is in A complement, which means X does not belong to A. So X does not belong to A means Fx is not equal to Gx. So this means your Fx is not equal to Gx. Now Fx is not equal to Gx. X was a member of X. Where will be Fx? F of X will be in Y. Where will be Gx? G of X will be in Y. So that means Fx and Gx are two members of the set Y and they are not equal. Also, Y is given to be a T2 space, that means Hausdorff space. If in a Hausdorff space there are two members which are not same, which are distinct, by definition of Hausdorff space you can find two open sets, one containing Fx, other containing Gx, and their intersection will be phi. So by the definition of Hausdorffness of Y, there exist open sets, G, H in Y. These will be the open sets in Y such that your Fx belongs to G, your Gx belongs to H, and intersection of these two open sets G and H is phi. Now your Fx is in G, your Gx is in H. From here I can say your X belongs to F inverse G, because Fx belongs to G. X will be a member of F inverse G. Similarly, Gx is in H, that means X belongs to G inverse H. Now X is in F inverse G. X is also in the set G inverse H, that means F inverse G intersection G inverse H will also contain the element X. So you can say your X belongs to F inverse G intersection G inverse H. One thing again to note, that your G and H are open sets. G is an open set in Y, H is an open set in Y. So G and H are open sets here. G and H are open sets here, and the function is continuous. You know that if a function is continuous from a topological space X to the topological space Y, then inverse image of every open set here in Y is open in X. So that means F inverse G is an open set. G inverse H is also an open set. So if I name it as K, then one thing is clear, that K is an open set, because this is an open set, this is an open set, and we know that intersection of two open sets is also an open set. So K is an open set in X. So K is an open set in X. We have taken X belonging to A complement. We have obtained an open set K such that X belongs to K. Only thing remains to show that K is a subset of A complement. If X becomes a subset of A complement, what we will have? We will have X belongs to K. Okay, and next I am going to show that K is a subset of A complement. This I will show now, that K is a subset of A complement. We have taken X belonging to A complement, and we have obtained an open set K such that X belongs to K and K is a subset of A complement, and this is enough to show that A complement is open. And A complement is open means A is closed. So our theorem will be finished. The only things remains to show that K is a subset of A complement, and that what I am going to prove now. I am going to prove that K is a subset of A. So K is a subset of A. To prove that K is a subset of A, what I will do, I will take one element Z from K and I will show that Z belongs to A complement. So let Z belongs to K. Let Z belongs to K. what was K? Your K was F inverse G intersection G inverse H. This was your K. So Z belongs to this set. If Z belongs to the intersection of two sets, this means your Z belongs to F inverse G and your Z also belongs to G inverse H. Now, Z belongs to F inverse G directly implies that your F of Z belongs to G and your G of Z belongs to H. Fz belongs to G and Gz belongs to H. But intersection of these two sets G and H is phi. So that means this element cannot be equal to this element. So this clearly implies that Fz is not equal to Gz because one of them is an element of G, another one is an element of H, and the intersection of G and H is phi. So how can these two elements be equal? So they cannot be equal. So Fz is not equal to Gz. And if Fz would be equal to Gz, then by the definition of the set A, your Z will be in the set A. On the other side, your Fz is not equal to Gz directly says that your Z belongs to the complement of the set A. So here Fz is not equal to Gz, that means Z belongs to complement of A. You have taken Z from the set K and you have obtained that Z belongs to A complement. That means you have shown that X belongs to K. X belongs to K was already we have proved. And now I have proved that K is a subset of A complement. I have taken X belonging to A complement and I have obtained an open set K such that X belongs to K and K is a subset of A complement, which means A complement is an open set. And A complement is an open set directly implies that A is a closed set, and that is what we require to prove. So this theorem we have proved. Now there is an extension of this theorem. An extension is that I'm writing the statement here. If F and G agree on a dense set, E, then F is equal to G. Actually, what I'm having additional here in this statement, that now F and G are agreeing on the set E. That means you are indirectly saying that your A is E. Your A is E now because F and G are agreeing on the set E. The only additional thing is that your E set is a dense set. What you are having F is equal to G on E. This you are having. And you are also given that E is dense. And E is dense means your E bar is equal to X. Your E bar is equal to X. But just now we have shown that the set A is a closed set. A and E are the same thing because now I am denoting A by E. So that means your E is a closed set. And for a closed set, your E bar is equal to E. So what you are having, your E is equal to X now. Your E is equal to X means F is equal to G on E, but E is equal to X. So your F is equal to G on X. And what is X? X is the whole set, the universal set in this case. And if F is equal to G on the universal set, that directly means that F is equal to G. What was required to be proved. So here is the first theorem of the day, and now we will move on to another theorem. The next theorem on Hausdorff spaces will prove that the statement, first I am writing the statement of the theorem. The statement is a convergent sequence, in a T2 space. T2 space means Hausdorff space. A convergent sequence in a T2 space has a unique limit. It cannot have two limit points. This we are to show, prove. So let X top be a T2 space and let Xn be a sequence in this topological space X top. What we are to show that this Xn converges to a, so let Xn be a convergent sequence. You can say, you can directly take it as a convergent sequence. What you are to show that Xn has a unique limit point. So Xn converges to a unique point. On the contrary, if possible, suppose that Xn is having two different limit points. So let, if possible, your sequence Xn converges to X and your sequence Yn converges to Y, where X is not equal to Y. X is not equal to Y and both are the points of your space X. But your X toy is a T2 space, X is not equal to Y. So you must have two open sets G and H, one containing X, another containing Y, and their intersection is Y. So therefore there exist open sets G and H such that X belongs to G, Y belongs to H, and G intersection H is Y, because the space X toy is a T2 space. Now your Xn converges to X. Xn converges to X means there will be some n1, you can say there will be some n1, such that for every n greater than or equal to n1, your Xn will be in the neighborhood of X, that is G. The particular neighborhood I am talking about is G. So I am using the definition of convergence now. By the definition of convergence, there must be some n1 natural number such that for every n greater than or equal to n1, we have Xn belonging to G. This is because Xn converges to X. Similarly, your Yn is converges to Y and Y is having a neighborhood H. So there will be a stage, you can say n2, such that for every n greater than or equal to n2, your Xn will be a member of H. So there exists n2 natural number such that for every n greater than or equal to n2, we have Xn belonging to H. Now what you are having is, after n1 every Xn belongs to G, after n2 every Xn belongs to H. Take maximum of these two. Let M be the maximum of n1 and n2. Then, since for every n greater than or equal to n1 your Xn belonging to G, and for every n greater than or equal to n2 your Xn belongs to H, and M is the maximum of both n1 and n2. So if your n is greater than or equal to M, obviously n will be greater than or equal to n1 also, and n will be greater than or equal to n2 also. So for every n greater than or equal to m, what will happen? Your xn will belong to G and your xn will also belong to H. So you can say your xn belongs to G and your xn belongs to H for every n greater than or equal to m. That means your xn belongs to G intersection H for every n greater than or equal to m, which is a big contradiction because your G intersection H is phi. How many infinitely many xn's be the members of G intersection H if G intersection H is phi? So this is not possible. We arrive at a contradiction, and this is a contradiction because why? Because our supposition is wrong, and we have supposed that the sequence xn in a Hausdorff space has two limit points. So it cannot have two limit points. The limit point of a convergent sequence in a Hausdorff space must be unique, and that was the proof of this theorem. So this was the second theorem of the day, and I'm stopping the topic here. We will be once again here with more and more theorems on Hausdorff spaces. Till then, wait. Thank you all.